Great, fantastic. Yeah, it's really a pleasure to be here. And I have to say that we have the coolest prime minister ever. And he's even cooler than you can think of it. Great, so it's my pleasure to be here. And I'm going to try to throw some light into the life of a self-driving car. So first, let me start by saying, why we potentially might want to have self-driving cars in the first place. Unfortunately, there's more than 1 million people a year that actually die due to traffic accidents. So imagine the potential impact that we can have if we can reduce that number significantly. As the population gets older and medicine gets better, we are having more and more issues of mobility. So self-driving cars can definitely help us out a lot. We should decrease our pollution, right? Our planet is not getting healthier. And what I'm most excited about self-driving cars is really try to think about what are new ways to do public transportation that will allow us to commute faster and in a much better way. And if you think about it, having a car is really a waste, right? So we should be thinking of sharing resources, both materials as well as space. So for those of you that own a car, so your car is bored to death. It's basically sitting around 95% of the time, just maybe talking to the car next by, right? And so imagine, the space that that car is taking, right? We could use that for parks. We could use that to make our cities much better. So you probably all have seen some way, or one of these systems, for example, the Google car, the Uber cars, et cetera, somewhere in the media, right? And these systems are really good at doing things like localization, path planning, avoiding obstacles. However, there is two problems that these systems have that prevent them from scaling up to a case where each one of us can actually use a self-driving car. Mainly, they use this thing on the top that typically is spinning. It's a lidar. And that thing costs these days around 100,000 Canadian dollars, right? So that's really expensive. And they use pre-recorded, manually annotated maps. And just, for example, to map the whole US, it's going to take around $1 to $10 billion. So imagine, having maps up to date. Now, so the goal of my research has been to try to create solutions to autonomous driving which rely on cheap sensors, okay, as well as little prior knowledge as possible. And this is actually possible, right, because us as humans can actually solve this task. And what do we use? We use our eyes, right? So we can, the same way we can actually use cameras in order to try to solve this problem. Now, from the point of view of computer vision, right, which is trying to use computers to understand the world via cameras, we have to solve many, many different tasks to do self-driving cars. We need to recognize the environment. We need to be able to estimate three-dimensional representation of the world. We need to be able to know how our car is moving and the other cars. We need to know what is happening in front of us, right? Understand motion and intention of those cars. And we need to do this in 3 dimensions. And we need to, again, understand everything that is in the scene that we see. Now, if we want to do this, what do we need to do? So first of all, we need data. And this might sound something that is easy, but it's not so easy because having access to one of these platforms costs already $500,000, right? So it's not something that you can just buy in the supermarket. Also, it's very important to think of the role of machine learning. We cannot handcraft rules that will represent all possible scenarios for a car. We need to be able to learn by driving, by example. We also need to think about models that are able to solve the many, many, many tasks that we need to solve for doing self-driving cars. And it has to be efficient, right? These systems have to react to this scenario. And they have to be real time. And this implies working on software. I'm a computer scientist, but also in hardware solutions for this. So in the remaining of this talk, I'm going to just tell you a little bit of what we have done in the spectrum of making self-driving cars affordable for each one of us. So I mentioned data at the beginning, right? So 7 years ago, we started trying to think of, OK, we want to work on this task of self-driving cars. Can we actually do that? And it turns out that it was not possible because we couldn't have access to any data sets, right? So this was, we spent the first 2.5 years actually building the benchmarks for people to compete in order to build the next generation of algorithms that will solve autonomous driving. So here you see the car that we use for this. We basically mounted with 4 cameras, this LiDAR spinning on the top, as well as GPS and IMU. And we went around and drive, in this case, the city of Karlsruhe. Okay? So let me play you a video. So here is the car in the parking lot of KITTI. So this is as I say, Karlsruhe. This is in collaboration with one of the labs over there. And, and as I said, we went around and drive, around easy scenarios, not so easy scenarios, where we have illegal maneuvers, to, really crowded scenes. And then use these fancy sensors to create ground truth in order to evaluate how well we can do with just cameras. Okay, so here you see examples of ground truth for depth, ground truth for how the vehicle moves, as well as to the detection and tracking. Okay. So this benchmark was actually a huge success, and it's still the only benchmark out there for self-driving cars, despite that it's been online for now almost 5 years. We have more than 20,000 folks actually working on this, and more than 500 submissions to the benchmarks, where basically every car company and every group working on this is actually working with our data. So let me tell you a little bit of what are the tasks that one needs to solve for self-driving cars. So the first and canonical one is actually trying to just reconstruct the environment without necessarily understanding what is in front of us. Right? So this is a task that as humans we solve all the time. We have 2 eyes, right? So this, imagine you have 2 cameras, and we want to reconstruct, right, for every pixel that we see in our eyes, right, how far away it is from us. Right? So this is basically, one of our latest algorithms that is able to, up to 40 meters, be almost as accurate as this really fancy laser scanner, while costing, a camera these days costs $30, right? Okay, so then once we reconstruct the environment, we need to perceive, understand what it means, what is in front of us, right? So one of the tasks that one needs to solve is pixel labeling, right? So for every pixel, in one of those images on the left, you want to be able to say, okay, is there a car there? Is the road there? Is there a person? As well as the thing that you also need to understand is being able to discriminate between every one of the individuals, every one of the cars that is out there. So systems right now using convolutional nets, using deep learning, as Anya was talking about before, are able to generalize really well to unseen, in this case, unseen scenes from different cities and create incredible results in terms of performance. This is only using a single image as input. Once we are able to understand pixels, we need to understand 3 dimensions, right? We need to be able to predict trajectories of the traffic participants. And this is what you see over here. So this is our latest results that were actually done by a 3rd-year UofT undergrad, right? Which is basically showing state-of-the-art results better than any of these car companies. So what you see here is you see trajectories in 2D and in 3D that the system is able to estimate, again, in places that the car has never driven before. So it doesn't require to use maps or anything. It's just given the images, it's able to estimate this. Next, we can, oops, interesting. Maybe you can close that. So next, we can actually estimate everything that is happening in the scene. So what you see here is a single camera mounted on top of the car. And basically, we developed the algorithms that are able to translate that image, that video, into a representation of the scene where you can actually do control. Right? So you see here in black the eco car, the car that is driving autonomously. You see the rays of the field of view, what the car sees. And you see that it's able to compute maps on the fly, and it's able to estimate where every single car participant is in the scene. Now, it's color-coded by the intention of those cars. And on the bottom left, you can see the traffic scenario without looking at traffic lights. So basically saying, what is the allowed set of maneuvers that our car can actually do safely? Another task that we need to solve is actually the task of self-localization. Right? If we want this vehicle to be able to drive us around, it needs to know at every point in time where it is in the scene. I need you to click on the slide. Yeah, thank you. And so the way that typically this is done in industry is that so a car manually drives around the world, and everything that it sees is stored in a data set. Okay? And then when it's driving autonomously, you look in your data set, where have I seen a place that looks exactly the same as what I see in front of me? Okay? So it's a bit like web search, right? So this works fairly well, but it's not scalable. Right? Imagine that you need to capture how the world looks like at every point in time, in every season, every time of the day. There is construction all the time, right? The world changes. So this is why doing self-driving cars is also very expensive, right? So what we look at is, can we actually create solutions to localization where we don't need to know the appearance of the world? And as humans, right, we can do this. We can navigate, and then we never know how a particular street, like Bloor Street, looks like, right? So it turns out that, yes, you can actually do this, and it's very simple. You can download freely from the web OpenStreetMaps, which is these maps that you see in blue in the screen. And what you can basically do is estimate the trajectory of the car, of the Ego car, by using just the cameras. And the motion of the car is enough to tell you where you could potentially be in the scene. So at the beginning, we're going to have a region of interest where we know we are more or less there somewhere. And it's going to be a uniform distribution, right, because we don't know where we are. And as we start driving around, then we're going to shrink the probability distribution of possible locations where the car could potentially be. Okay? And this is what you're going to see on the bottom right in a second. Just for comparisons, in black, you're going to see what the ground truth is. Okay? So the beginning is uniform. You see a few modes, but very quickly, it's able to say, we're exactly in this location. Okay? So you see here just a zoom in of the same idea. Right, a few modes, and very quickly there's only 2 modes now, and we turn left, therefore there is, this is the only location where we could potentially be. And this, you can download the maps from the web. It's free, right? You don't need to pay anything. Just mount 1 or 2 cameras in your car. So here is a more Manhattan-like scenario. So you see that in this case, there is 2 modes of the distribution, right? It's very symmetric, but again, at some point we do a maneuver that is only one possibility. Let me just zoom into different regions. Sorry about that. So what you're going to see now is the same thing, but in a map that is the whole city of Karlsruhe. There is 2,000 kilometers of potential roads, okay? Which means that there is a lot of uncertainty of where you could potentially be in the scene. And with only 30 seconds of driving, it's able to localize very accurately where you are in the scene. Okay, so hopefully you can see that in the screen, right? Again, very quickly, it says, we are in this highway here. This is where we are. The mode is relatively big. And at some point, we take an exit, and then it shrinks to very precise location of this is where we are. Thanks. So I mentioned before the mapping was very expensive, right? And the reason why is just the way that people are actually tackling this problem. However, if we could potentially have affordable solutions to mapping, then we should be able to use those maps that are up to date. So why is this so expensive? So this is what car companies are doing these days. And you probably have seen one of these in the city. So the idea is that you have a car, you mount it with a whole bunch of fancy sensors, and then you drive around the world, and then you capture how the world looks like again. Right? So it has very small coverage, and it's really expensive. This is what the car sees, right? It sees a minuscule part of the world. Right? However, there is so many other ways to see the world that we could use in order to improve the coverage of our maps. One example, right, is Big Brother, right? It sees us all the time of what we are doing. Right? So we could use drones, UAVs, planes, satellites go around the world twice a day, every single day, right? So it's very, very up to date, the imagery. Now, it's not so trivial how to estimate maps from just aerial views. Okay, so hopefully, thanks. So what you're going to see here is a system that is able to, as it drives and using aerial views, localize where the car is in terms of the location in geocoordinates, and is able to also map, create HD maps of where are the roads, where are the lanes, where the parking spots are in yellow here, as well as in blue, where are the sidewalks. Okay? So this is really efficient. It takes 3 seconds per kilometer of road. So in a simple computer cluster, you can actually map the whole world. And so again, for mapping, the problem is the same as it was for self-driving cars, that, again, only companies that can really afford this have access to data. So one of the last things that, the most recent things that we have done in the lab is actually to create the next big benchmark for people to compete into creating maps in an affordable manner. And the cool thing is that actually we selected, Toronto area to be the main area, right? So the way that we created this was by going to the government and going to the libraries and using the HD maps that have already been created. And these are really, really rich. They have all sorts of very interesting metadata. So we have 3D buildings of the whole Greater Toronto, as well as the location of every single tree, the location of every single pole, the shape of every traffic light, every pole in the city. Right? And the idea is that now we want participants to be able to estimate all these different things automatically. And we also generated, using, again, deep learning neural networks, solutions that are able to estimate these maps. So here you see our latest results using only aerial views, right? So they are almost as good as the ground truth. We can estimate, interesting. We can estimate the topology of our streets. And I mentioned before that, for the localization, we use these OpenStreetMaps. These are generated by people clicking in aerial images the location of streets. And we are only 1% below what people do for this task. And it's fully automatic. So you can imagine, and we can do this at a larger scale of the whole world. So you can imagine the impact of doing things like this. Other things that we can do is create centimeter-accurate maps from just Google Street View panoramas, which are available out there for the whole world as well. Okay, so just to conclude, I show you a couple of things that one needs to do in order to create self-driving cars for each one of us. So things like sensing, perception, localization, mapping. I show you our latest, coolest project into bringing Toronto to the community at large. And there is many, many, many things to do in research in order to really solve all the different tasks for self-driving cars. And I just want to acknowledge the fantastic team that is behind what I show you today. And I just want to finish also with a promise that we will have self-driving cars in Toronto really, really soon. Thank you.